Students, welcome to my YouTube channel. In this lecture, I am going to answer questions from sample paper 6 of RK Bali navigation book. The last they have given some few sample papers, 7 sample papers. So I have picked sample paper 6 and I'm going to answer all the questions from that particular question paper one by one with detailed explanation. So let's begin with question number 61. What scope code should be entered while crossing an FIR region? So, out of the three options given, option number A, 7500, it belongs to unlawful interference with the operation of aircraft. Okay, that means hijack. 7600 means radio communication failure. Scope code 2000 means in the UK airspace. If you are entering UK airspace from any airspace outside the supervision of United Kingdom, you have not been assigned any transponder code by the previous ATC under whose supervision you were flying in, you will set transponder code 2000. Okay, so the correct option is option Charlie 2000. Scope code should be entered when crossing an FIR. When crossing an FIR, if no code has been given previously. Okay, so option Charlie. Question 62. What does the pitot tube measure? Total minus dynamic pressure, total plus static pressure, dynamic plus static pressure. So, this is the pitot tube in your aircraft. Okay, so this is the pitot tube mounted on the left wing of your aircraft. In case of big aircraft like airlines, you will have pitot tube located on both sides of the fuselage near the beginning of the fuselage, that is nose section. Now, there are three pressure instruments: altimeter, vertical speed indicator, and airspeed indicator. Out of these three, as you can see over here, altimeter and vertical speed indicator, these two instruments work mainly and only on static pressure. Okay, only on static pressure. The third pressure instrument, which is your airspeed indicator, this instrument works on both static pressure and pitot pressure. Static pressure and pitot pressure. Okay, so what does the pitot tube measures? First things first, pitot tube is only related to airspeed indicator. Is only related to airspeed indicator. Okay, next thing. Now this pitot tube, let's say this is your pitot tube. Okay, this is your pitot tube. Now when aircraft moves in the forward direction, the relative airflow will create a pressure in front of the pitot tube. So let's say, just for explanation purpose, if this is your pitot tube, and there is airflow, relative airflow coming from front. This relative airflow will create an impact pressure in front of the pitot tube. It will create an impact pressure in front of the pitot tube. This impact pressure is nothing but your dynamic pressure. And this dynamic pressure is nothing but proportional to the airspeed indicator reading that is shown on your airspeed indicator. Now, this is your, let's say, consider this is your airspeed indicator. Okay. Now, in this airspeed indicator, there are aneroid capsules, and these aneroid capsules are directly connected to the pitot tube. Okay, are directly connected to the pitot tube of your aircraft. And this airspeed indicator also works on static pressure. So let's say there is a static pressure line entering here. There is a static pressure line which brings or introduces static pressure in the instrument. Okay, static pressure. So I will close this instrument now. Okay, so static pressure is fed directly in the instrument, and pitot pressure is fed in this aneroid capsule. Pitot pressure is fed in this aneroid capsule. So whatever pressure is sent by the pitot tube, that pressure is called pitot pressure. Now this pitot pressure is nothing but a combination of dynamic pressure, like I explained before, plus static pressure, because static pressure is the normal atmospheric pressure is dynamic plus static. Okay. Now this dynamic and static pressure will be fed in this aneroid capsules, and this aneroid capsule will be surrounded by static pressure being fed by the static pressure line. Now if you want to get airspeed indicator reading, in order to get airspeed indicator reading from your airspeed indicator, you need dynamic pressure. You need dynamic pressure, right? You need dynamic pressure. But now this aneroid capsule has two things entering inside. They are dynamic and static, and it is surrounded by what kind of pressure? Static pressure from the outside. Now static pressure outside this aneroid capsules in the instrument will be the same as the static pressure entering inside this aneroid capsule from this pitot pressure, right? Static pressure surrounding the aneroid capsule will be the same as the static pressure entering the aneroid capsule through pitot tube. So the effects produced by both the static pressure from outside and from inside the aneroid capsule will be the same. And therefore, this both the static pressure, one from outside, another inside, both static pressures cancel each other out, and finally we are left with dynamic pressure. We are left with dynamic pressure only, right? And this dynamic pressure is responsible for expanding and contracting the aneroid and contracting the aneroid capsule. And this expansion and contraction of the aneroid capsule will be transmitted in the form of levers, mechanical linkages, and the airspeed indicator pointer will move accordingly. So the correct answer here is, what does the pitot tube measure? It measures dynamic pressure and static pressure. We get rid of the static pressure by feeding static pressures around or inside the back case of this airspeed indicator instrument. Next, if pitot source gets blocked during descent, ASI will dash, altimeter will dash, and VSI will dash. Now, first things first, like I explained here, altimeter and vertical speed indicator work only on static pressure. They do not work on pitot tube or pitot pressure. So, automatically you will eliminate option alpha, and we are left with option Bravo and Charlie, which states that altimeter will be not affected. VSI will also be not affected by pitot tube blockage, because VSI and altimeter both depend on static pressure, not pitot source or pitot tube. So irrespective of pitot tube working fine, functioning properly or getting blocked, it doesn't matter to a altimeter and VSI. So we are left with Bravo and Charlie, overread, underread. So what will happen to ASI? Now when pitot source gets blocked, airspeed indicator behaves like an altimeter. Behaves like an altimeter. Meaning, let's say situation 1. When you climb, your altitude increases, and therefore your altimeter will register this information and show increase in altitude, shows increase in altitude. Whenever you descend, altitude of your aircraft will decrease, and your altimeter show a decreasing trend in altitude. Show a decreasing trend in altitude. Increase in altitude means values will increase 2000, 2500, 3000. Decrease in altitude means values will decrease 2000, 1500, 1500, so on and so forth. So similarly, ASI will behave like an altimeter, meaning whenever you descend, the values on your ASI indicator will start decreasing. When you climb, the values on your ASI indicator will start increasing. Okay, so meaning it behaves like an altimeter. You descend, the value also descends or decreases. You climb, the value shown by ASI indicator will also increase. So you may be flying at 100 knots, but just because you are climbing to a higher altitude, the airspeed indicator will show you your indicated airspeed 120 knots, 130 knots, more than what is necessary. If you are descending, okay, and during your descent, your indicated airspeed, the correct speed of your aircraft is, let's say, 100 knots. But just because the pitot tube is blocked, ASI will behave like an altimeter, and instead of showing 100 knots airspeed, it will show a decreasing airspeed, meaning 90 knots, 80 knots, 60 knots. Okay, so what do we call this? So when ASI behaves like an altimeter in descent, it will start showing smaller and smaller values, even if your airspeed is stable. So that means it will underread. It will underread. Instead of showing 100 knots correctly, it will show 80 knots, 90 knots, something like that. So we call this underreading. When you are climbing, okay, when you are climbing at 100 knots, ASI indicator will show some value more than 100, 110, 120. So we call this overreading. We call this overreading. So the correct answer here is you're descending in here. So during a descent, your ASI will underread. Okay, it will show a lesser value. Next, question number 64. Forward CG will cause what? Forward center of gravity. Okay, so you must remember all the characteristics of aircraft with a forward CG, characteristics that aircraft will display when the CG is to its aft limit. Okay, so what happens when your aircraft is when the CG of your aircraft is at forward limit, okay, too far ahead. So what will happen? Your aircraft becomes nose heavy. Aircraft becomes nose heavy. So instead of, and when it becomes nose heavy, it will tend to pitch down because the nose is heavy. So aircraft will tend to pitch down. So in order to stop that from happening, the pilot will have to pitch up a little extra, okay, and maintain higher angle of attack to have some extra lift in order to compensate a nose heavy compensate for a nose heavy aircraft. Now when you increase the angle of attack of your aircraft, increase angle of attack of your aircraft, you will get closer to your stall speed. You will get closer to your stall speed. Let's say your stalling speed is 100 knots. Okay, so as you keep increasing the angle of attack of your aircraft, your airspeed will go closer and closer to the stall speed, meaning your airspeed will start dropping. It will start decreasing in value. Next thing, aircraft becoming nose heavy. Aircraft becoming nose heavy is same as adding some extra weight to your aircraft. Extra weight to your aircraft. And when weight increases, as a consequence, your stall speed also increases. So if in normal conditions, like in normal CG conditions, when the CG is not too far forward, too far aft, your normal stall speed is 100 knots. But in such conditions like this, your stall speed will increase to, let's say, 130 knots. Okay, so that means you have lost extra 30 knots. 130 minus 100 is 30 knots. That means you have lost extra 30 knots which you could have used during your cruise for your cruising speed, right? So the margin between your cruise speed, if your normal cruise speed is, let's say your cruise speed is 150 knots. With this stall speed of 100 knots, the margin between your cruise speed and stall speed is 50 knots. And with this new stall speed of 130 knots, now the margin between the difference or the margin between your cruise speed and stall speed becomes 150 minus 130, 20 knots. The margin has decreased. From 50 it has become to 20, right? So this becomes more unsafe. So adding it's like, so whenever you add extra weight to your aircraft or when the CG of your aircraft is too far forward, these are the dangers that it invites. So you have to be careful about that, and the option here will be forward CG will cause higher stall speed, like here, like I explained here. Stall speed will increase from 100 knots to 130 knots. Aircraft flying a track inbound parallel to airway direction of 090, compensating 5 degrees starboard drift, 12 nautical miles starboard of the track. What will be the ADF reading when it is tuned to a destination NDB, which is 45 nautical miles away? So that means there is an NDB station here. Okay, the current track to the NDB is at 090. Okay, so step 1, let's find out the heading of aircraft. Step number 1, starboard drift. Means heading will be less than track. Heading is 5 degrees starboard. Track is 090. So heading of this aircraft will be 090 minus 5, 085 degree. Step 2. Step 2, apply 1 in 60 rule. So NDB is 45 nautical miles away. This is your NDB. Aircraft is 12 nautical miles to the right hand side. Right, 12 nautical miles to the right hand side. That means track error is distance of track divided by distance gone into 60. So 12 into 60 divided by 45 is 16 degrees. Track error is 16 degrees. Okay. So step number 3, original track was 090. Step number 3, original track to the NDB station is 090. From the current position of aircraft, which is over here. So from the current position or from the present position, aircraft back to the NDB station will be equal to original track minus track error. Why minus? Because your aircraft is over here and we will have to make a left turn. From this position we will have to make left turn in order to go to a NDB station. Because if we are to the right hand side, NDB is to a left hand side and we have to go to the NDB station. That's why minus. Whenever you make left turns, you subtract. So original track is 090. Track error is 16 degree. So 090 minus 16 is 74 degree. So new track to the NDB station is 074 degree. Step number 4. Step number 4. So new track to the NDB station, if I have to draw that track, it will look something like this. New track to the NDB station will be 074. So step 4, track to the station is equal to relative bearing plus heading. Now track to the station is 074. Relative bearing is what we have to find out. Heading of aircraft is 085. Heading of aircraft is 085. Therefore, relative bearing will be equal to 074 minus 085 is 011 minus 011. So plus 360 will give you 349. So the relative bearing of your aircraft will be Charlie 349 degrees. 349 degrees. Simple. So with this question, I will stop here. I will do the next 5 questions in my next video lecture. I hope you have understood these 5 questions. Practice them. If you have any doubt, let me know in the comment box. Do watch secondary surveillance radar lectures that I have uploaded to my channel. In addition to that, I have also solved all track and drift questions, VOR questions, NDB questions. Do watch them also. You will find them in suitable playlists. I have made separate playlists for all. So you will find those video lectures over there. All the best.